So welcome in this new video. In this video we will be discussing about different traversals in binary tree or in general any tree, and we will also look into some lesser known trees. And with no further delay, let's get to today's topic. But before that, I want to just emphasize that if you haven't watched the previous video, then do check it out as well, because it is having topics of importance for this binary tree as well, because it is covering some properties of binary tree as well as some lemmas that are important. So do check it out from the I button popping at top right of this video. So let's now get to today's video content. So first of all, we will see what is BFS and DFS, then we will see some other variations of lesser known trees. So what BFS stands for is breadth first search, and basically it is known for searching an element in a tree using the breadth first traversal. And DFS means depth first search, that is also a kind of searching for an element in the binary tree via the depth first traversal. So we have to see today what are these traversals and how to do these traversals. So breadth first traversal is also known as level order traversal, that I discussed in previous video as well, but we will see it in here as well. So in level order traversal or breadth first traversal, we have to go level by level to traverse. So in this, the BFS traversal for this tree will be 1, then 2, then 3, then 4, then 5. So you can see it here as well. Now we will come to depth first traversal. So depth first traversals are of three types. First is in order traversal, second is pre-order traversal, and third is post-order traversal. So basically we will first see what pre-order traversal is. So it means that whenever we traverse a tree, then we will first consider its root element, then we will consider the left element, left child, and then we will consider its right child. So you can see here that if we traverse this tree in pre-order traversal, then we can say that we can have the 1 as the root, so we have to write that. Then we can consider this whole tree as the left child, so we have to then first do in here as well, we have to traverse this as well. So again we can write 2 as the root of this subtree, then we will write its left subchild like let. So we can write in here as 4 as its left child, then we will write as 5 as its right child. Then as this is completed, so we will go to right of this main tree, so that is 3. So you can see it in here as well. See, in similar fashion, whenever we have in order traversal, then the root element will be coming at the middle position. So first we will see the left child, then the root, then the right child. So the traversal in this case of this particular tree will become, first we will have this left child, in that also we have the subtree, and in that left child will be there. So 4, then root, that is 2, then 5, that is the right child, then we will have 1 as the main root, and then right of the main tree is 3. So 4, 2, 5, 1, 3 will be the answer. Next, the post order traversal, the root element will come at the last, so we will have the left, then right, then root. So you can see in here that the traversal for this tree will become, in the post order will be, left will be this one, so 4, then right, that is 5, then 2, then we will, as we had to do this left subtree because we have to first do the left of this main tree as well. So the subtree was in the left of this main root, so we had to do this one. Then we will see the right of the main tree, so 3, then the main root node, that is 1. So the traversal becomes 4, 5, 2, 3, 1. Okay, so you can also see that why do we care for this. There are many tree questions that can be solved using any of the above 4 traversals. Like examples of these questions can be like finding size, maximum, minimum, print left view, etc. So basically all these 4 have order of n time complexity, and the difference is only in the extra space that is required. So in the BFS, that is breadth first traversal, there is order of W maximum width, that is like order of W time complexity, where W is the maximum width of binary tree. So in here we basically use Q to store the elements whenever we traverse. And in depth first traversal we have order of H, where H is the height of that binary tree, and in here we use tech for implementing depth first traversal. And maximum width of binary tree at a depth or height H can be 2 to the power H, and here we consider that H starts from 0. So the maximum number of nodes can be at the last level, and worst case occurs when binary tree is a perfect binary tree with numbers of nodes like 1, 3, 7, 15, etc. Hence we see that the worst case the value of 2 to the power h will be equals to the seal of n divided by 2, where n is the number of nodes in the tree. And as you also know that binary tree is having a balanced binary tree is having order of log and height. Okay, and in a skewed tree where we a skewed tree can be looked like, let's say you have this tree in here. Then if you just remove this left child of this main tree, that is 2 1 and 3 elements from here, then what we will have is a skewed tree. That it skewed tree can be basically thought as that we have a child that is having a child at only one side of the tree. It can be either left 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 or right 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 right. So in this case if we remove 2 1 and 3, then it will be at right 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 right. So 3 4 and 5 can be seen as a skewed tree, and in this case the height in the worst case will be order of n. Hence for both of these cases order of n will be the extra space required, but worst case occurs for different types of trees. Like it's evident from the above points that extra space required for level order traversal is likely to be more when tree is more balanced, because it will be having a broader tree, and the extra space for depth first traversal is likely to be when their tree is less balanced, so it will be having a more skewness type of thing and it will go to more depth. That's why. So when to choose which one? So basically when you have a problem that has to search something that is more likely closer to the root element, then we should prefer BFS, breadth first search or traversal, in the case of searching an element. And if the target node is close to a leaf, then we should prefer DFS, that is depth first search. Now coming to the tree traversals once again, just to see if there is anything left. Yeah, one interesting thing to note is that in case of binary search trees, in order traversal gives nodes in non-decreasing order, that is in an ascending way. Okay, so if you want to get the elements in a descending order, then we have to just reverse the values of the in order traversal. Okay, and you can as well see that we can use pre-order traversal to create a copy of the tree. Okay, also it is used to get the prefix expression of an expression tree, so we will look what is an expression tree as well in this video only. And post-order traversal is used to delete the tree. Also we can use it to get the postfix expression of an expression tree. Okay, now coming to the foldable tree, or you can say a foldable binary tree. So it is a tree which can be folded from the root element, and it is kind of a symmetric tree. So either you call it a foldable binary tree or a symmetric tree, it means the same. Okay, so you can see that in these two examples, this first one is a symmetric tree and it is also foldable from this middle side, and this is not a symmetric tree and it is also not foldable. So here also they have given 4 examples where these two are foldable, and C and D, that is these two are not symmetric, hence they are not foldable. Okay, now coming to continuous trees. So a tree is a continuous tree if in each root to leaf path, that is, or like whenever we traverse from root to all the leaves, then whatever paths are possible, so in each path absolute difference between the adjacent keys or elements or nodes will be only one. So in this example you can see that all the elements, let's say whenever we traverse from root to leaf, that is 3 2 1 3 2 3 3 4 and 5, so all are having one difference between adjacent nodes. 3 to 2 is having one difference, 2 to 1 is having one difference, 2 to 3 is having one difference, 3 to 4 is having one difference, and 4 to 5 is having one difference. So this is a continuous tree. But let's say you are given this example, so you can see that whenever we go from 7 to 5 and 6, so 7 to 5 is not having absolute difference as 1, and again when we go from 7 5 and 4, again the 7 and 5 are not having absolute difference as 1, and again when we go from 7 8 and 10, so 8 and 10 are not having absolute difference as 1, hence this is not a continuous tree, and this should be true for each and every element to be a continuous tree. So this condition should be true for each and every element. Now coming to expression tree. So expression tree is a binary tree in which internal node corresponds to the operator and each leaf node corresponds to an operand. So like you can see that this is an operator: plus, star, minus, divide, okay, multiply, and modulus, or like that. And these are the operands: 3, 5, 9, 2. Okay, so whenever you have this kind of tree in which the internal node is having the operator, or you can basically say that the root is an operator, and the childs are operands, then this is an expression tree. So you can evaluate this expression tree via the in-order traversal, post-order traversal, and pre-order traversal. So let's say you can also do this if you have to evaluate this one. So you will first start from the bottom, then go up. So 80 plus 20 will give us 100 as our answer. So you can see in here, this is our answer as well. So I hope you understood some of the basics of these trees and other lesser known trees and how to traverse in a tree. So this was it for today's video. Until the next video, keep learning and keep watching.
Uncovered.